So take a moment to consider the chair you're sitting in, the coffee you're drinking, and the air you're breathing. Solids, liquids, and gases are all made up of atoms, and we think of atoms as being particles. Other things like light and sound we consider as waves. Waves and particles seem to be very different. However, all matter has the potential to act both like a particle and like a wave. The wave nature of a single atom is incredibly small and nearly impossible to observe in a controlled way. But if we cool a large cloud of atoms down to near absolute zero, which is the limit where all atoms stand still, the wave nature emerges. Our atoms in their final state are 1/1000th of a degree above this limit. So in our lab, we start with a hot gas of single atoms, and then we cool them using lasers and magnets. One such cooling technique is known as evaporative cooling. As an analogy, consider a steaming cup of coffee. The hot atoms rise from the surface, leaving the coffee with less energy, and it slowly gets cold. When we blow over the top of the coffee, we're able to cool it more quickly. We use the same type of concept in evaporative cooling, except now, instead of a coffee cup, we have a magnetic bowl filled with atoms, where the hot atoms zip around the top, and the cold atoms settle near the bottom. We then use radio waves to blow away the hot atoms, leaving us with an ultracold atomic gas. When reaching these ultracold temperatures, an atomic gas enters into a new phase of matter, known as a Bose-Einstein condensate, or a BEC for short. A BEC is an object which is large enough for us to observe with a microscope and manipulate, yet is completely governed by the laws of quantum mechanics. We use BECs to model a wide variety of complex physical systems which would otherwise be difficult to study in a clean and tunable environment. One peculiar property of BECs is that they flow without viscosity, meaning there's no internal friction within them, and that makes them a superfluid. As an example of how we can study the properties of superfluids, we prepare a BEC so that it has a long cigar-shaped geometry, and then use a repulsive laser beam to push the BEC. When we do this, we see the buildup of atoms forming a bulge or a plateau just before the piston. We attribute this buildup to the generation of quantum turbulence within the region, which we can observe when we image the BEC after expansion. This observation of quantum turbulence in a superfluid gas is currently at the forefront of modern physics. And one thing we learned from this experiment is that the superfluid nature greatly depends on the parameters of the experiment. Ultimately, understanding the fundamental nature of these macroscopic quantum systems will help to shape the future of nanoscale electronics, quantum computing, and cosmology. Thank you.